I'm Professor Lakshmi Ravishankar, and today we'll be discussing about electrocyclic ring closing and ring opening reactions. So at the end of this module, the student should be able to understand the two modes, namely the con-rotatory and the disrotatory modes of electrocyclic ring closing or ring opening reactions, and also predict whether a given polyene would undergo con-rotation or disrotation to give the desired product. A quick recap of what we have done in the previous modules, which would help us to understand this module better. We have seen how to identify whether the reaction is a ring closing or ring opening, and also determine the number of electrons which are participating in the electrocyclic reaction. We also saw how we can draw the molecular orbitals for ethylene, butadiene, hexatriene and the allylic systems, how to identify the HOMO, and how to identify the symmetry element of an orbital with respect to the mirror plane and the C2 axis of symmetry. So an electrocyclic ring closure is essentially cyclization of an acyclic conjugated polyene system such that the terminal carbons interact to form a sigma bond. It will proceed through a cyclic transition state which could involve either 4n electrons or 4n plus 2 electrons. We consider butadiene going over to cyclobutene. This is an example of a 4n system, whereas hexatriene going over to cyclohexadiene is an example of a 4n plus 2 electrons, because this has got 6 electrons participating in this reaction. Several theories have been put forth for predicting the outcome of a pericyclic reaction, and all of them necessitate that the lobes of the reactant molecular orbitals must be of the correct sign in order for bonding to occur in the transition state, which would eventually lead to the formation of the product. We will be concentrating on the frontier molecular orbital theory, which was simplified by Fouquet further. And according to this, one need not have to consider all the molecular orbitals of a given polyene system. We only need to look at the frontier or molecular orbitals, that is the orbitals which are participating in the reaction, and which are these: the highest occupied molecular orbital or the HOMO, and the lowest unoccupied molecular orbital or the LUMO. Woodward-Hoffmann came out with a set of rules after studying several pericyclic reactions, and according to them, a pericyclic reaction can take place only if the symmetries of the reactant molecular orbitals are the same as the symmetry of the product molecular orbital, which essentially means that the lobes of the reactant MOs must be of the correct sign in order for bonding to occur in the transition state so that the product is formed. So the stereochemistry of an electrocyclic reaction is essentially determined by the symmetry of the polyene HOMO. So we need to identify the HOMO, and in thermal conditions the ground state is my HOMO, whereas under photochemical conditions one of the electrons from here is shifted to the excited to the next first excited state, which now becomes my new HOMO. Quick run through how to identify a HOMO and its symmetry. If you have n-p atomic orbitals, then you will have n molecular orbitals. If n is even, like in butadiene where you have 4p orbitals, then the HOMO will be half of that, or psi2 is my HOMO. If for octatetraene, psi4 becomes the HOMO. If n in psi-n is odd, like psi1, psi3, psi5, etc., the molecular orbital will have the terminal lobes of the same face coming on the same side, which would be symmetrical with respect to the mirror plane and asymmetric with respect to the C2 axis of symmetry. But if n in psi-n is even, like psi2, psi4, etc., the molecular orbital will have the terminal lobes of the same face on the opposite side, or the molecular orbital will be asymmetric with respect to the mirror plane and symmetric with respect to the C2 axis of symmetry. So essentially we are talking about these two kinds of systems where you have the lobes on the terminal carbons. Here the same face is on the same side, here they are on the opposite side, and in order for a bond to form, these outermost lobes must rotate so that there is a favorable bonding interaction, and let us see how that is possible. So if I have this situation where the two lobes of like sign are on the same side, in order for a bond formation, this will have to move in this direction, this will have to move in an opposite direction, or the terminal lobes will have to rotate in the opposite direction, and Woodward called this a disrotatory ring closure, and you can see that you have got a bond formation. But if I have a situation like this, where the like signs are on the opposite sides, then both the lobes will have to move in the same direction, either clockwise or anti-clockwise. Here it is the clockwise rotation shown in order for a favorable bond formation, and this kind of a motion was referred to as the conrotatory motion. So if we take an example of 2,4-hexadiene. So basically you have got 2 pi bonds, so 4 pi electrons. So you'll have 4 p atomic orbitals, 4 molecular orbitals. So Psi2 becomes my HOMO. And if you see the terminal lobes of the polyene system, you find that the like signs are on the opposite side. So this will have to undergo a conrotation for a constructive overlap resulting in a bond formation. If we were to consider a disrotation, you can see that it is a destructive overlap. This is not allowed and you will not get the bond formation. But what happens if I do the same reaction under photochemical conditions? One of the electrons from Psi2 is excited to Psi3, so Psi3 becomes my new HOMO. And now if you see, the terminal lobes have got the same sign coming out on the same side. So now this would undergo a disrotation in order for a constructive overlap. A conrotation under photochemical conditions, you can see, would not result in a constructive overlap. It would be a destructive overlap, and hence it is forbidden and not observed. Let us go further and consider the octatriene. So this is a 6-electron system. So the ground state, Psi3 is my HOMO, and if you see Psi3 is my HOMO, it is symmetrical with respect to the sigma plane. You have the like signs coming out on the same side. So this will undergo a disrotation to give me cyclohexadiene moiety. Please remember the law of microscopic reversibility applies here. So whatever is the nature of the rotation in the forward direction, be it con or dis, for the ring opening also it would be in the same direction. That is, microscopic reverse reactions also occur with the same disrotatory sense in this particular example. What would happen if the reaction is done under photochemical conditions? One of the electrons from Psi3 will be excited to Psi4. So Psi4 will become my new HOMO, and you can work out and see what type of rotation will favor the ring closure under photochemical conditions. We can also extend it to the 5-atom electrocyclizations, the well-known Nazarov reaction, whereas you have a cross-conjugated ketone going over to cyclopentanone under the influence of an acid. So this is 1, 2, 3, 4, 5. You have 5 p orbitals. So 5 p atomic orbitals, 5 molecular orbitals. 3 of them are shown here. You will have a 1 non-bonding. And since it is a carbocation, so 4 electrons have to be filled. So Psi2 becomes my HOMO. You see now that the terminal lobes have got the opposite face coming on the same side. So this will undergo a conrotation for cyclization. So Woodward and Hoffman came out with a set of rules after studying a whole lot of pericyclic reactions based on the number of electrons involved and whether it is under thermal or photochemical conditions. So if I have a 4n electron system, under thermal conditions it is the conrotation which is favored, under photochemical conditions it is the disrotation which is favored. But if I have 4n plus 2 system, then photochemical is favored by con and thermal reactions will take place using by this rotation. The same thing has been simplified in a TEC method to determine the type of ring closure, which is an EC tip. T stands for thermal, E stands for even number of pi bonds, and C stands for conrotation. So if the reaction is thermal and has even number of pi bonds, then the electrocyclic reaction will be by conrotation. If I change any one of T or E to photochemical, that is P, or O, that is odd number of pi bonds, the resulting electrocyclic reaction will proceed by disrotation. However, if both T and E are changed to P and O, then the reaction will proceed by conrotation. So to summarize, we'll have to examine the interactions that occur in the HOMO as the reaction proceeds in order to predict the outcome. If the overlap is constructive, that is the same phase, the reaction is allowed. If the overlap is destructive due to different phases, then the reaction is forbidden. Depending on whether the orbitals have to move in the same or the opposite directions for an overlap to occur, you can have two modes of electrocyclic ring closing, namely conrotatory and disrotatory respectively. If the terminal lobes are of the same phase, it will involve disrotatory motion, and if they are of the opposite phases, then it will involve conrotatory motion. In the next module, we will be seeing some more examples of conrotation and disrotation and predict the stereochemical outcome of electrocyclic reactions under thermal and photochemical conditions. Thank you.